Hello and welcome along to some revision material based for the September assessment. We used this PowerPoint in 2020 and it's also applicable to the 2021 assessment that you're currently studying for. If you're watching this in the future, it's the similar material, hence why I've probably not edited it again. So if we look at the discrete distributions first of all, you have your standard DPD, otherwise known as discrete probability distributions. It's usually in the form of a table. It could be a straight line graph illustrating how likely an event is for separate outcomes. And because it's separate outcomes, that's why it's a discrete probability distribution. You do need to know that the mean, the expectation of x, is the sum of x times p. This is also the case for e of x squared. So instead of x times p, it would be x squared times p. The variance of x is expectation of x squared minus mean squared, your mu squared, but your mean is the expectation of x. So I've just written there, sigma squared, variance of x, is e of x squared minus e of x, all squared. So that bracket is important. There's two different ways of e of x squared. I try to sometimes illustrate that by a pause. So you've got e of x squared, which is the first variation, and then you've got e of x squared. That's the second variation. So that formula gives you variance. If you need the standard deviation, you will square root. So let's have a go. This is taken from the Legacy spec from 2012. We've got Newville Athletic Football Club, and they win half of their matches, and you can see 3 points for a win. 3 points for a win, so half their matches, so 0.5 is a probability, and they lose 20%. So if we put 20%, the chance of getting 0 points into the table, and what's left over, it's going to be 30%, 0.3. Okay, part B. Let's calculate the mean and standard deviation. Now, because here it asks for standard deviation, our need to know formula for the variance, we will eventually need to square root, hence why it's worth a little bit more marks than usual. So let's start off with the mean, expectation of x. We have x times p, and we do this for 0 times 0.2, plus, because sum, 1 times 0.3, plus 3 times 0.5. Which comes out at 1.8. So that is our mean. We expect them to get 1.8 points on average. Our need to know formula involves e of x squared, so we repeat this process but squaring x this time. So e of x squared, so 0 squared times 0.2 plus 1 squared times 0.3 plus 3 squared times 0.5. Make sure it is x squared. If you type that into your calculator, you get 4.8. Now that is not our variance. Our variance formula is another need to know. So we need to know e of x, we need to know e of x squared. We also need to know the variance formula. E of x squared minus e of x squared. That pause is to illustrate how it is e of x, the mean, all squared. So that 1.8 goes there at the end, and we're going to square that 1.8. So 4.8 subtract the 1.8 squared comes out at 1.56. Now, that is our variance formula that we've used. The question asks for standard deviation, so we need to make sure that we square root, which is 1.25 points to 3 significant figures. Okay? State the probability that the number of points awarded to Newville Athletic after a home match is more than 1 standard deviation above the mean. Well, 1 standard deviation above the mean, 1.8, plus 1 sigma, 1.25, is 3.05. The probability of them getting more than 3.05 is impossible. 3 is the maximum amount of marks. So mean plus 1 standard deviation, 3.05, more than 3.05 is impossible. It's not an outcome. So probability 0, hence the word state. All right? And there's the mark scheme to confirm. Here's another one for you to have a go at. Feel free to pause the video here and have a go yourself. spoiler warning, here come the answers. You were warned. You should have paused it by now before to have a go. Okay, straight into mean. So x times p, using our need to know formulas. So 40 times 0.37 plus 70 times 0.18 plus 100 times 0.14 plus 140 times 0.12 plus 190 times 0.19 comes out at 94.3. We repeat this process, but it's x squared times p, so 40 squared times 0.37 plus 70 squared times 0.118 plus etc. And really there we're getting the mark for the working, not the answer, because the answer was given. Part 3, find the standard deviation. So variance first of all, so e of x squared, that 12,085, subtract the 94.3 all squared. E of x squared minus e of x squared. So your variance comes out at 3,192.51. Square root that for standard deviation comes out at 56.5. Yeah, that square root shouldn't go that far, so 56.5. More than £1.20. £1.20 is 120 pence. There are two options, so 140 and 190. Add those two together, hence 31%, 0.31 as a probability for more than 1.2. Exactly 1.2 is not an option. It's not one of our listed options. Therefore, it is impossible to get exactly 1.2. Not because it's impossible to get equals. No, it's because it wasn't one of the outcomes. If the question was, what's the chances of exactly 140? That would be 0.12. It's an option. Whereas £1.20 is not one of the options listed. The table only includes passengers who pay fares, children under 5, and senior citizens travel for free. If we included these zero fares, would the mean be larger, smaller, or the same? Well, 0, if we included 0, that would be a negative outlier, and that would drag our mean down. So because 0 is less than the current mean, our mean would reduce. Hence smaller. The reason would be because 0 is less than the current mean. Okay, let's have a look at binomial now. Things to remember, you've got two parameters, so x squiggle or tilde, x tilde, b, np, not quite politically correct, that's an old school reference there for you. But when you define your binomial, you have two parameters, the number of trials and the probability. On your calculator, you press dist, binom. BCD can be used all the time. Even for equals, you could put 3 lower and 3 upper. But yes, BPT for the exacts, precises, and the BCD for the continuouses. What's fantastic about the new calculators is you have lowers and uppers as well. The mean and variance formulas are in the formula booklet, and that's illustrated here. So n times p and n times p times 1 minus p for variance. If we wanted standard deviation, we would square root. It does talk about a probability calculation, but we don't need that. We've got the graphical calculator. So here's a question, and I've already illustrated the first answer. So it refers to English breakfast. English breakfast is the first probability listed. So for a sample size of 16, you define your distribution as 16 and 0.45, the 0.45 because of the English breakfast. Exactly 5, so BPD5 using 16 and 0.45 as your parameters will generate the probability you require of 0.112. You can also do that in BCD, 5 lower, 5 upper as well. It wouldn't be worth 3 marks, it would probably be worth 1, and you're probably going to get asked one of these questions, not all. Okay, 50 guess, so n is 50 this time, but I read continental breakfast. So continental breakfast is the second option. So English breakfast was the 0.45, continental is the 0.25. Oh, so this is just me illustrating the BPD. The issue is this is the old calculator. So when it comes to BCD, that might be an issue. Okay, less than or equal to 12. Thankfully, the old calculator only has uppers. So upper because we want at most 12. At most 12. So if you have a look at the calc, BCD upper. Make sure we change that number of trials. So BCD this time. Number of trials is now 50. and the upper option is 12. The lower option on your calculator would be 0. Make sure we change it to 0.25 because of continental breakfast. For part 2, no breakfast, and that's the last option there of 0.3. So still with the sample size 50, more than 10, fewer than 20. Now, the calculator is going to come on the screen, but I'm going to skip it because unfortunately it doesn't have lower and upper. But what I will do is this, a number line to illustrate. Because I want more than 10, I actually want 11 as the lower. Because I want fewer than 20, not including 20, 19 will be the upper. So in your BCD, 11 will actually be the lower and 19 will be your upper. So can you confirm on your calculator BCD, 11 lower, 19 upper, using 50 number of trials, and because it's no breakfast, 0.3. That should be 0.836. Okay, so requiring breakfast. It hasn't specified what type of breakfast, just simply that they require a breakfast. Two ways you can go about where this 0.7 comes from. They either have a full English or a continental, hence 0.45 plus 0.25, or requiring a breakfast is the opposite of not requiring a breakfast. So 0.3 away from 1 is also 0.7. This time it's for 40 guests, so 40 is your number of trials and your probability is 0.7 because it just says requires breakfast. And it asks for mean and standard deviation. So looking at the form booklet now, n times p and n times p times 1 minus p for the variance. So n times p, just simply 28. We would expect 28 guests, 70% of 40, to require breakfast. This time for the variance, n times p times 1 minus p. So we're also going to times by 0.3. Gives us 8.4 as a variance. Read the question carefully. It requires standard deviation, so square root for 2.9. Okay, here's your opportunity to pause the video. Have a go at this question yourself. You have been warned. If you don't want to know the answer, make sure you pause it now. Okay, here we go. So, cash 0.22. Sample 24. So we've got a number of trials 24 with a probability 0.22. If we go BPD 2 using 24 and 0.22, that would be worth a nice 1 marker. That would be 0.0565. Now we're on to debit card 0.45. This time for a sample of 40. Fewer than 20, we're actually going to put 19 as the upper, 0 as your lower. More than 15, you're going to put 16 as your lower, and 40, or a very large number, as your upper. At least 12, at most 24, they are actually the values we want. Because of the phrasing at least and at most, we do indeed require those. So your probabilities are thus, using 19 as your upper, using your 40 and 0.45 with 0 as your lower, then 16 lower, 40 upper, 0.786, and 12 to 24, 963. Now, part C, it goes on to talk about credit card. Now, we don't know the proportion of credit card, but we are told that they pay by cash, debit, or credit, so it's the remaining probability. So simple subtraction, 0.22 and 0.45 is 0.67. That away from 1 is 0.33. So if we use 0.33 as the proportion for credit card users, n times p gives us a mean of 66. N times p times 1 minus p, so times by 0.67. You could use a bracket, 1 minus 0.33 n bracket there. Gives us a variance of 44.2, and that is the question complete because it does indeed ask for variance. Last type of discrete probability distribution we're going to cover here, and that's the Poisson distribution. It's very similar to how you type it into the calculator. You've got your PPD option and your PCD option. There's only one parameter, lambda. Lambda is your mean, your constant average rate. So you're looking for that word, constant average rate. What's beautiful is the mean is also equal to the variance. So lambda, being the mean, is also the variance. If it ever asks for standard deviation, you would square root your lambda. So here we've got an example. You've got X, Y, and Z. Battery, exhaust, and is it tyres? Yes, it's tyres. Part A, find the probability during a particular hour that any particular hour, so each one of these says per hour, per hour, per hour. Any particular hour, there are fewer than 2 buying battery. Battery is X. So X less than 2. So 1 will be your upper. Because it says fewer than 2, you don't want to include that 2. So make sure you put 1 as your upper in your PCD. Now, for part B, it talks about during a particular 4-hour period. And we're talking about exhaust. So 3.5 for 1 hour, 3.5 times by 4 for 4 hours. So we would expect 14 customers. What's the chances of exactly 8? Using 14 as your lambda, you mean exactly 8. So 8 is your X in your PPD, or lower and upper in PCD, to achieve that probability of 0.0304. Find the probability that during a particular hour there is a total of more than 15. Total, X plus Y plus Z. We need to assume that X, Y, and Z are independent for this calculation to be correct. So X plus Y plus Z for 1 hour, so no multiplication is required. 2.8 plus 3.5 plus 5.7 is 12. And because it says more than 15, 15 isn't actually going to be your lower. 16 will be. So 16 is your lower, 1 times 10 to the 10 as your upper, because there's no limit to a Poisson. There is no limit to an exponential. So upper bound is 1 times 10 to the 10. Your lower needs to be 16 for that 0.156. Why is Poisson unlikely to provide a suitable model? Well, for the number of tyres, not the amount of customers, but the number of tyres. You tend to buy and sell tyres in multiples, don't you? Yeah, you tend to replace all 4, or there tends to be an offer, buy one, get one half price. So the event of one tyre to another tyre is not independent. People tend to buy them in groups. Yeah, the event of customers, not customers, okay, but tyre to tyre, okay. Tyres or other product not independent. So tyre to tyre, okay. There can't be an infinite number of tyres. I get that. So Rickle, you can criticise that. It has to be in context. You can't just say mean not constant or something along those lines. Customers tend to buy tyres in more than one at a time. Tyres will be sold in multiples, so not independent. That's a requirement of Poisson. There's your 2 marks. The garage has limited stock, so not limited, not limitless. And of course, unlikely to be constant through the day, something along those lines. So me personally, I would go with the top 2 here. So yet again, here's a question for you to have a go at. Pause the video now, have a go before the answers are revealed. Okay, you were warned. We have coins. Coins are a rate of 1 per 10 meter square. In any 10 meter square, so we're using 1 as the average rate, at most 2 will be your upper using your 1. Exactly 4, again, PPD using your 1. And your probabilities are 0.920 to 3 significant figures and 0.0153 to 3 significant figures as well. Determine the probability that more than 8 are found in 100. Now, 100 meter square is 10 lots of your 10 meter square. So times your 1 by 10, so 10. You need to tell the examiner that you're now using lambda as 10 rather than 1. Because the interval has been multiplied by 10, therefore your expectation has been times by 10. So using 10 as your lambda, not 8 as your lower, but 9. So use 9 as your lower because it's more than 8. So you carry on with 9. 9 is your lower. 1 times 10 to the 10 is your upper. This will probably be worth 2 marks because your calculator does lowers now. 0.667 is what you're aiming for. Brooches. Now, brooches are 1 per 50. And because brooches are 1 per 50, they will be 2 per 100. Because part 1, it's referring to total. So we're going to add these two together. But it's talking about total per 100. So we know there's 10 coins on average per 100. And there are 2 brooches per 100. So that's a total of 12. We're expecting 12 coins slash brooches in 100. At least 15, so 15 will be a lower. Again, that'll be another nice little 2 marker for us. So using 12, because you double your 1, because you're doubling your 50 to 100, your interval needs to be consistent. So 50 to 100 is double. So 1 times 2 is also 2. You've got your 10 from part B, 10 plus 2, hence the 12. Use your 12, 15 is your lower, 1 times 10 to the 10 is your upper. 0.228 is what we're aiming for. Sometimes Romans buried a hoard of coins together. Now, because coins are found together, because they're buried together, they'll be found together. State with a reason which of are unlikely to be a better poisson. Brooches are more likely to be a poisson because the coins, they fail on the independence criteria. Because coins are buried together, you are likely to find coins together. Therefore, finding one coin next to another coin affects the event of them being independent. Therefore, brooches are more likely to be a poisson. Okay, if we look at continuous, for the purpose of the revision for September, we're not going to do rectangular. We've done a separate video on rectangular, so if you'd want to practice rectangular distribution for practice for your exam in June, then by all means have a look at that video. Here we're going to look at just the basic normal distribution, and we'll have a look at the exponential distribution as well. Normal. Because it's a continuous curve, any continuous probability question, whenever you're asked for exactly, it's impossible. Now, yes, there is an NPD button, but do not press it. NPD does not do exactly. What it does is it does a rounding error. It does a continuity correction. It goes 0.5 either side. So don't ever press NPD. NCD is the only button you press. You'll type in your mu for your mean, you'll type in sigma for your standard deviations, and these parameters, okay, you've got to be careful because it asks for sigma first. If a sample is taken and it refers to a sample mean probability, make sure you use standard error. I'm sure recently you've been doing errors and power, so you'll be familiar that sample means have a slightly different distribution. They have standard errors instead of standard deviations. So let's have a go. Mean 57.15 goes as a mu, sigma 0.04. So if we go NCD, and we type into our calculator a lower of minus 1 times 10 to the 10, because 57.2 will be our upper, we're going to type in sigma 0.04 and then mu 57.15. So you make sure you type them the right way around. So 0.894 for part 1. And if this time we have a lower of 57.1, I'll be honest with you, you'll be asked for one of these, and whichever one you were asked for would only be worth 1 mark. So lower 57.1 and upper 57.2 with your sigma first of 0.04 and mu 57.15. 57.1. 0.15. 0.789. Okay? The tricky bit is part B. We've been taking a sample, alright, but be careful. All less than. We've got the probability of an individual ball being less than 57.2. That was A part 1. That's the event of one ball. Let's say ball number 1 satisfies that criteria of being less than 57.2, and ball number 2, and ball number 3, and ball number 4, all the way up to, and ball number 16. You'd be timesing 0.894 by itself, by itself, by itself, by itself, 16 times. Now, instead of typing 0.894 16 times into your calculator, separated by a multiplication sign, you can just use the power button. So whenever you come across an all question, you raise the individual probability to the power 16. For this one here, 0.116. Because for part 2 it says mean, we have a completely different distribution now. We don't have a standard deviation of 0.04. We have a standard error of 0.04 divided by the square root of n. N for this question here is 16, which is a nice 0.01 instead. So on your calculator, if you put 0.01 as your sigma, still with 57.15, greater than 57.16, that will be your lower. 1 times 10 to the 10 is your upper, will give you 0.159. So 57.16 as the lower, 1 times 10 to the 10 is your upper. And I'm just going to show you how to type in sigma. So yes, 0.04 divided by the square root of n, the square root of 16 for this question, because it said mean. Sample means have standard errors instead of standard deviations. Okay? Pause the video, have a go at this question. Okay, you were warned. Type in mu as 185, and above that, sigma 10, less than 200, so 200 as the upper, minus 1 times 10 as the lower, more than 175, so 175 lower, positive 1 times 10 to the 10 as the upper, and then part 3, lower and upper. Like I said before, these will be worth 1 mark each now on the new syllabus because of the nature of the calculator. Part B is very likely to still be 4 marks. So part 1, 0.933, part 2, 0.841, and then part 3, 0.774 something. So whether you've left it as 0.774 or whether you've rounded it up depends on the accuracy. Either is acceptable. Part B is probably definitely worth mentioning because it's a sample, because n is 4. Sigma, when you type sigma into your calculator, make sure you type in 10 divided by square root of 4. What I don't like about this mark scheme is they've done the variance of the sample distribution rather than the standard error of the distribution. So 10 over root 4 is what you're going to type into the calculator there. 190 is the lower, still 185 as your mean, should give you 0.159 as well. And to round things off, the exponential distribution. The mean of and the variance of an exponential are indeed in the form booklet, reciprocal. And the reason why it's reciprocal is because you're asking the question opposite to a Poisson. Instead of how many times does something happen in an interval, it's a question of how long of an interval until your next success. You're flipping a Poisson on its head, hence reciprocal for the mean. Key point to remember, the parameter for exponential, lambda, is still the same lambda from a Poisson. So that Poisson mean, Poisson parameter, exponential parameter, is the lambda you use in the probability formula. It has to be less than or equal to. If it's a more than, you've got to use the formula, but then take away from 1. If it's an in-between, you use the formula twice and do a subtraction. And because it's continuous, the value you see is the value that you use for x. Okay? So yeah, be very careful with that. Students sometimes try to overcomplicate the reciprocal 1 over lambda because it doesn't mention mean at all. The lambda you are told is the lambda you use. Let's have a go. Okay, so light bulbs were told lambda equals. Now T is in thousands of hours. So the mean, 1 over lambda, I think comes out at 80. But it says in hours. The mean of T would be 80. T is measured in thousands of hours, so in hours, so 1 divided by, or fraction, is 80. Now that's the mean of T. However, because T is measured in thousands of hours, to get both marks, we've got to write it as 80,000 hours. Now, if you didn't spot it in part A, you would definitely spot it in part B, because if you sub in 100,000, the probability ends up being ridiculously big, pretty much 1. 100,000 hours, the value of T here is 100. For part 2, the value of T is 50 and 150 respectively. Less than is the correct way round. So on the calculator, we're going to use this formula, 1 minus, because it's a less than. Less than or equal to, it doesn't matter because equals is impossible because of the continuous nature. So 1 minus e to the minus 0.0125, because that's lambda, times by t, or x, in this case 100. So let's have a look at the calculator. 1 minus e, which is shift ln. It's an ln. Logarithm natural is what it stands for. Negative lambda, 0.0125, times by x, in this case t, of just 100. Not 100,000. Because t is measured in thousands of hours, the value of t there is 100. Probability 0.713. This time we've got an in-between. What we'll do is we'll work out less than or equal to 150 and get rid of less than or equal to 50. So what we do here is we do 1 minus e to the minus lambda, 0.0125 times by 150. Here I've actually worked them out separately. You can use brackets. You'll notice the probability you get for less than or equal to 150 will be bigger. So what is that 8466 minus 4647? Because I want in between those answers, that's why we do the subtraction. So 382 to 3 significant figures. You can type both in as one calculation separated with a minus using brackets if you wanted to. And that's what the mark scheme's done here. The reason why I've worked it out separately is because there is a technique in chapter 19, Goodness of Fit, where you might actually find it beneficial to work out 150 and 50 separately. But that's for a later day. Okay, security lights 15 in a new office blocks. These security lights are permanently switched on. Find the probability that all 15, so something to do with probability to the power 15, working 365 days later. We're measuring in thousands of hours. How many thousands of hours are there in 365 days? So 365 days times by 24 hours. 24 hours is 8,760. Because it says are still working, that means they break after this amount. So because this is a more than, we do 1 minus this probability. Notice how I'm using 8.76. Now this gives me the probability that one of them is still working after a full year. Because it says all 15, just like with the normal we did before, bulb number 1, bulb number 2, times by, times by, times by, times by, we're going to use power 15. So I'll just repeat that again. We've converted days into hours, 8,760. Working after a year, so they break, the lifetime is longer than, more than. So I work out 8.76 thousand hours. Take that away from 1, because I want more than. And because each of the 15 bulbs, all of the 15 bulbs are still working, hence why that probability is raised to the power 15. There's a few variations, but yeah, 0.9193 is the correct answer there. Hopefully you found this video useful. Best luck in your exam in September.